Hello, welcome back to Learning Chemistry with me, Jaya. Okay, now in this video, we're going to continue our discussion about chapter 1, which is particulate nature of matter. So this is the part 2, okay? Now, in the part 1, we already learned about what is matter and then what are states of matter and how they behave, how the particles behave, and also the change of state and what happens to the particle when there's a change of state. Okay, now today we are going to continue the discussion about the particulate nature of matter, and let's start with a heating curve or cooling curve. Yeah. Now, what is a heating or cooling curve? So, from the name, we can already know that heating curve is just a curve that represents or show us the relationship between temperature and time. All right. So, to understand the heating curve, what is going on in the heating curve, we need to understand the shape of the curve itself. Now, let's start with the beginning of the curve, which is here, right? As you can see here, the temperature is negative 25 degrees Celsius. Now, at this point, we must know that the water is in solid form because water freezes at 0 degrees Celsius. So below that temperature, it has to be in the state of solid. So it is ice. Then if we heat the ice, of course, what will happen? The temperature will increase. Okay? So the ice will warm up. So that's why the curve would look like this. As the time passed by, the temperature would go up. Okay? Now, at 0 degrees Celsius, which is the melting point or freezing point of water, of pure water, the curve becomes horizontal line. What does that mean? It means that at zero, when it reaches 0 degrees Celsius, there's no increase or there's no change in temperature. It just stays 0 degrees Celsius. So what happens in this process? Yes, in this process, there is a change of state. Okay, there's a change of state because 0 degrees Celsius is a melting point of water, so the ice would melt at this point. Got it? Now, after the ice all melted up, melted down, yeah, around here, then there's no ice left. There's only liquid water. Oh, okay? There's only liquid water. Now, when we keep heating the water, it will certainly increase in temperature. That's why the water starts to warm up. Okay, it starts to warm up, and after it reaches 100 degrees Celsius, the temperature will stay, will be constant at that temperature, which is 100 degrees Celsius. Now, why this happens? Why it stops at 100 degrees Celsius? Because 100 degrees Celsius is the boiling point of water, of pure water. So at this point, there will be a change of state from liquid to gas. All right. And then after all the liquid water has been evaporated or boiled off, then what remains is the gas or the water vapor, right? At this point, there's no liquid water left. There's only water vapor or steam. Then it will goes up in temperature as we keep heating it. Okay. Now the question is why there's a horizontal line, or this temperature stays the same at melting point and boiling point. Okay, if you remember from the change of state that we have learned previously, yeah, when a solid melts into a liquid, they start moving, correct? For the solid particles to start moving, to become particles in liquid, they need energy. They need energy to move. Just like you, when you want to do an activity, for example, you need to eat first. You need the energy from your food in order for you to be able to be active, right? So it's just the same with the particles. They need energy for them to move from solid to liquid. So what happens here at the melting point is that all the energy that we give into the water or into the ice will be used only for the change of state, not to increase the temperature. All right? It also this it also applies to the horizontal line, which is in the boiling point. When boiling happens, the particles of liquid turns into the particles of gas. Yeah, the differences between the two is that in liquid, the particles move slow, and in gas, particles move very fast. Okay? Now, in order for the particles to move faster, it needs energy. Again, it needs energy. So the all energy that the liquid water receives from us will be used to change state, not to increase the temperature. That's why it becomes a horizontal line in which there's no change of temperature. And now that explains why in the heating curve and cooling curve there are always the diagonal line, which represents the change in temperature, okay, and then the horizontal line represents the change in state. Okay, got it? Now, if you are very focused, well, you will see that here it is written some evaporation occurs. Why can evaporation happens when it doesn't touch the 100 degrees Celsius, you might ask? So that will lead us to the differences between the evaporation and boiling. As I already promised you that I will explain it later, right? Now, let's discuss the differences between boiling and evaporation. So here, I've got the picture of boiling water, and this is actually fog or clouds. They are technically the same. Yeah, they are water vapor. So this represents evaporation. Okay, now let's discuss the differences between boiling and evaporation. Now, from the very obvious one first, from the appearance, what can you see? The difference. Yes, boiling has its like bubbles thing going on, right? So what bubbles in boiling indicate? Yes, it indicates that the change of state from liquid to gas in boiling happens or occurs in all parts of the liquid. Yeah. Meanwhile, evaporation only occurs at the surface of the liquid. So it doesn't happen in all parts of the liquid. What's more, boiling happens only at the boiling point. Okay. Now evaporation occurs can occur Now, evaporation can occur at any temperature as long as it's liquid. Yeah, as long as the substance is in a liquid form. And then one more thing about the difference between boiling and evaporation is boiling produces steam. It's actual mixture of steam and water vapor. Meanwhile, evaporation only produces water vapor. Okay, that's the product of boiling and evaporation. Okay, those are the differences between boiling and evaporation. Now, let's continue on with the phenomena found in matters. Let's start with diffusion. So, what is the diffusion? Okay, to understand what is diffusion, imagine you are spraying some perfume on your skin, and then after a while, someone across the room will be able to smell it. So what happens here? What happens to the aroma or the perfume particles that you spray on? Yes, it will spread. The molecules or the particles of your perfume will spread across the room. That's what the diffusion is. So diffusion can be defined as the mixing of particles to fill up the space. Particles across the space available. What is happening here? What caused the diffusion, really? So the diffusion is caused because particles are always in constant motion. Yeah, remember from our previous lesson that all particles are always in motion, but not arbitrary motion. The motion that is responsible for diffusion is moving of particles. Yeah, because particles are moving. So, because diffusion needs particles to move, it only happens in liquid and gas only. It doesn't happen in solid because particles in solid stay in place or they don't move at all. Okay, got it? So it only occurs in liquid and gas only. Got it? Yeah, that is the diffusion. Now let's continue on with the Brownian motion. So as I said before, that particles in liquid and gas are moving. All right. So the motion that are able to see that are able to be seen by microscope will look like this. The particles of, for example, like the pollen under the microscope will be like this. As you can see here, the particles of the movement of visible particles will be zigzaggy like this. Yeah. Now, this movement of visible particles are called the Brownian motion. Yeah. Now, what caused the Brownian motion? What caused this zigzaggy pattern? Now, this motion is caused by the collision between the visible particle with the particles of the invisible. So what is the invisible particles? The invisible particles are particles that are way too small to be seen. like the particles of air. So the particle of air, let's just draw the particles of air, right? Like this. It's very, very small. So small that we can't see under the microscope. But we can sense their presence uh, by the movement of the visible particles. For example, this is the pollen particle. Yeah. So the pollen, because it moves, it will collide with the gas particles, right? And because they are colliding with each other, then the pollen or the visible particle will be bounced off like that. Now that creates the zigzaggy pattern. This happens again and again and again, and that creates this zigzaggy patterns or this zigzaggy motion, which is called the Brownian motion. So that is the Brownian motion. Okay, now let's continue on with the gas particles. Closer look, up close and personal. So the particles in gas is very unique. That's why we need to look more into it. First, pressure. Let's start with pressure. So what is pressure? As you might already know that the gas particles move at a very random direction, correct? Now, there's a time where the gas particles will collide with the wall of the container, right? So when the gas particles collide with the wall of the container or the lining of the container, that will create a pressure. Yeah. So pressure is caused. So again, the pressure is caused by the collision between gas particles and the wall of container. So that is pressure. That what causes pressure. And now, when the volume of the container of the space is reduced, then the collision between the gas particles and the wall of the container will become more rapid, right? And that's when the pressure increases. So let's say we have this plunger thingy, and then we push the plunger like this, then the space for the gas particles to fill in will decrease, and that causes the pressure to increase due to more rapid collision between the gas particles and the wall of the container. Okay, got it? That's the pressure. Now, let's move on to the rate of diffusion of gas. We already talked about diffusion, right? So diffusion is the mixing or the spreading of particles in liquid and gas. Okay? Now, what is the rate of diffusion? The rate of this diffusion is just this, how speed or how fast, how quick a diffusion of gas happens. Okay? Now, the rate of diffusion of gas is dictated by two factors. First is the molecular weight, and the second one is the temperature. Why these factors affect the rate of diffusion? Let's start with the molecular weight. Now, imagine that you are asked to run from point A to point B. Okay? Now, it will be easy for you because you just run, right? And then what happens if you are being asked again to run from point A to point B, but this time you have to bring some books on your head, for example. let's say this is some books. The books weigh, let's say, 10 kilograms. Now you have more mass that you need to bring, right? And what happens? Will you run faster or will you run slower? Yes, logically, you will run slower with the same energy. Yeah, with the same energy, will run slower. Why? Because now you feel heavier than before. And so molecular weight will cause the same effects on particles. Particles with larger mass will move slower, right? And then the particle with higher, sorry, with lower mass will move faster. Now, remember that diffusion is caused by the movement of particles. So when particles move slower, the rate of diffusion, let's just abbreviate it into ROD. Yeah, ROD will slower, of course. And then when the particles move faster, the rate of diffusion will get faster. Got it? Okay. Now, the temperature. Now let's discuss why the temperature affects the rate of diffusion. I think it's easier to understand this. Temperature has something to do with the kinetic energy, right? The higher the temperature, the higher the kinetic energy of the particles. Remember, the kinetic is the Greek term, or Greek is derived from the Greek word, which means about movement, right? So as the temperature increases, the kinetic energy will also increases. When kinetic energy increases, the movement of particles will also increase. Then what happens? Then the rate of diffusion will also increases, and vice versa. Yeah. So that is why these factors affect the rate of diffusion in gas. It's actually not only in gas; it also happens in the liquid. Okay. Now this is the infamous. No, this is the famous example of how molecular weight affects the rate of diffusion. Now in this tube, there are two types of cotton wool. Now the cotton wool is just the same, but this cotton wool is soaked in ammonia solution. Ammonia is NH3, right? And then this cotton wool is soaked in hydrochloric acid or HCl. Now as you can see here, when the tube which is filled with the two cotton wool is left for a few while, then there will be a white smoke forms here. So what is the white smoke? White smoke is actually just ammonium chloride, NH4Cl. So as you already might guess, NH4Cl or ammonium chloride is formed when NH3 meets with HCl. And now, what can we observe from the experiment? What can we observe is that the white smoke, which is the ammonium chloride, is formed closer to the HCl or the hydrochloric acid, correct? That means that when ammonia has reached this far, the hydrochloric acid only reached this far. That means that ammonia diffuses faster than hydrochloric acid. Okay? Now, what caused this? What causes this is the MR, or the molecular weight of each molecule. The MR, or the molecular weight of NH3, is 14 plus 3. 14 is the AR of N, And then 3 is the AR of hydrogen times 3. So 3. 14 plus 3 equals 17. Meanwhile, the MR, or the molecular weight of HCl, is 1 plus 35.5, which is 36.5. Now, from this, we can conclude. So from this, we can conclude that as the heavier the particle, the slower the rate of diffusion happens. Got it? Okay, now let's continue on with a problem or with a question. Now here we've got a table, yeah, represent a gas, the formula, and also the relative atomic or molecular mass. And now let's answer the question. Let's start with A. Which two gases will mix fastest? Explain. Do you have any idea? Yes, the answer is helium. Why? Why is it helium that makes fastest? Because again, helium has the smallest MR, or relative atomic or molecular mass. Remember that the lighter the molecule or the particle, the easier for them to move. Hence, the faster the diffusion. Alright? And now let's continue with B. Which gas will take the least time to escape from a gas syringe? Now, this question is only a rephrase of the first question. Yeah. Take the least time means that it is the fastest to escape from a gas syringe. That means that the fastest diffusion rate or the fastest movement. Again, the answer is helium. Correct? Now, C. Would you expect chlorine to diffuse more slowly than gases in air? Explain. Now, chlorine has molecular mass of 71. Now, from this data, would you think that, or would you expect that chlorine will diffuse more slowly or faster than gases in air? Okay, the answer is it will diffuse slower. Explain why. Why this happen? Because we need to answer this. We need to take into consideration what is the gases in air. Now from the combined science that you already learned at grade 7 and 8, you will know that air is comprised mostly of these gases, which is oxygen and nitrogen, in which nitrogen is the most abundant gas in air, followed by oxygen. Now, because chlorine has higher or larger molecular mass than oxygen and nitrogen, we can conclude that chlorine will diffuse slower. So the answer for this, or the explanation for our answer, is because chlorine has larger molecular mass than gases in air, which are O2 and N2. And now let's finish it up with D. An unknown gas diffuses faster than nitrogen, but more slowly than methane, which is this. What you can say about its relative molecular mass. So we need to predict what is the relative molecular mass. But we don't need to be precise here. We just need the range. So, as you might already notice here, that the unknown gas diffuses faster. What can you conclude from that? Yes, the unknown gas, which let's just say it's an X gas, right? the mass of X needs to be lower or lighter than the molecule of nitrogen, which is N2. N2 has mass of 28. Okay, got it? Now, X diffuses more slowly, as you can see here, than methane. So from that, we can conclude that the mass or the molecular mass of X has to be larger than methane, which is CH4. CH4 has the mass of 16, right? So from this, we can conclude eventually that the mass of the unknown gas must be between 16 and 28. Or you can also answer it by a certain number. Anything that is between 16 and 28. You can answer it like, let's say 20 or 23 or 24. The thing is, it needs to be between 16 and 28. Or you can just answer it by a range like this. Okay, got it? Good. And I think we've come to the end of our lesson today. So, what we have learned today, we have learned about the diffusion. So, we have already learned about the heating curve and also the phenomena found in matters, which is comprised of diffusion and Brownian motion. We also have learned about the pressure and the rate of diffusion gas, what affects the rate of diffusion in gas. And also we have already answered a question. Okay, now if you have more questions regarding this chapter, you can ask me in the comment section. And if you find this video helpful, don't forget to subscribe and like this video. Okay, now and now don't you ever forget that you don't give up. And one last thing I need to remind you. Okay, I think that's all for today, and good luck for your study and just never give up. Okay, see you on the next video. Bye.